Okay, thank you very much for joining us in the part 3 of the webinars that we're doing on drip quality. What we did previously, or we've done in the last seminars, we've looked at the 5 features that you see in all dripper data that we give. Specifically, that is K and X, that is the exponent, KD, K, the turbulence coefficient, and the filtration area. So what do each of these mean? And in the first seminar, we explained what we mean by the turbulence coefficient. In the second one, part 2 of the webinar, we showed K, sometimes called A, and X, sometimes called B. What do they mean? We saw that the turbulence coefficient, we saw that in order to get water through a dripper, we needed to create pressure loss. And the pressure loss comprised a little bit of turbulence, a little bit of friction loss, a combination of the two. And in the dripper specifically, we wanted more turbulence. We wanted to create that washing machine effect and less friction loss. And turbulence we measured by the turbulence coefficient K. And we saw that the greater the value of K, greater the turbulence coefficient, the cleaner the dripper would be. And the turbulence coefficient, K, depends on the labyrinth depth, the width and the length. Length also concerns the number of teeth, and the design and manufacture of the actual labyrinth itself, including the teeth. And then in part 2, we looked at the relationship between dripper flow rate and pressure. We saw that it was the relationship was with that equation, Q equals K times P to the power of X. And this was the starting point of the hydraulic design of any irrigation system. This is the beginning point. And we saw that the lower the value of X, the pressure exponent, the better. And that would lead to, we could get away with smaller pipes, and we would have less flow variation. Now today, with webinar part 3, we're going to look at KD and we're going to look at the filtration area. So first of all, we start off with KD. Now, what the KD is, we call it the dripper local head loss. Now, where the KD, that local head loss, it can be put into a formula which you see on the left-hand side of your screen in the box, but that's not important at this stage. I just want to show you that it does go into a formula. And those of us, those irrigation designers who have got irrigation software, that formula is actually in their software. But what I want to just concentrate on today is not so much the technicality of that, it's the actual KD is the loss in pressure as a result of the dripper being in the dripper line. Now, if we just throw back to part 1, in part 1 we discussed how the pressure loss through a dripper comprised of friction loss and some turbulence. Okay, and the analogy that I gave was on the friction loss, we gave a laminar flow, water flowing down a slow moving canal. And that was our friction loss. And then in the right hand image, turbulence, that's that raging torrent that we see. And within the dripper, therefore we have a bit of the turbulence that I'm showing here and a bit of the friction loss. Okay, in the case of a dripper, we actually wanted more turbulence. The more we could get, the better. Now, if we now look at dripper lines, okay, a dripper line pressure loss is also a combination, but instead let's just take out the turbulence and we get the local head loss. So the pressure loss going through a dripper line comprises your friction loss and your local head loss. And the local head loss is what we call the KD. Now, if I just look here, if you can see the top diagram, you've got flow through a dripper line without drippers, and underneath it we put in the drippers. Okay, so now you can see that there's a disruption to the flow. All features that we have looked at until now have concerned the dripper only and not the dripper line. but now we're actually looking at the dripper line itself. The dripper effectively blocks up a part of the dripper line, and it impedes the flow and increases the pressure loss just by its very presence. The greater the proportion of the inside cross-section taken up by the dripper, the greater will be the local head loss, and the greater will be the value of KD. So let's just have a look at this. The smaller a dripper's inside diameter, the greater the proportion of the inside cross-section the same dripper will take up. So if we just look at this, the inside cross-section, that's the area inside these circles here. And the black shaded part is what's taken up by the dripper. So you can see if we take the same dripper and we put it into a smaller pipe, this black shaded area will take up a greater proportion. And therefore, the smaller the pipe, the greater the KD. Conversely, if we take a larger dripper size, the larger the dripper size, and put it into the same dripper line diameter, the greater the proportion of the inside cross-section that the same dripper will take up. So again, we look at the cross-sections here. Now, all these cross-sections, these three that you see, that's the inside of the circle, they're all the same, but now we're going to use bigger drippers. There's a smaller one, going to a bigger one, going to a bigger one. So this one here on the right that I'm pointing to now, that will have the higher KD. And just to put some names to these, we have the Aries dripper, and the DripNet PC, and Uniram. Okay, so if we put all of these into the same pipe diameter, the Uniram will have a higher KD than the Aries will have. Now the values of KD, the higher values at the upper end will be 1, sometimes more than 1, and the lower values of KD, when it almost makes a little bit, no significant impact, it's a tenth of that, 0.1. Let's have a look at the 5 Netafim drippers. Uniram, DripNet PC, on the left-hand column here, Aries, Typhoon Plus, and Streamline X. Now I go over to the right-hand column. These are the KD values. And then the second from the right, we have the internal diameters. So if we take Uniram, now Uniram goes into inside diameters that vary from 14.4 to 17.5 millimeters. So as the diameter increases, so the KD value reduces. From at the top end in a smaller pipe size, the KD of Uniram is 1.2. And then we put it into a slightly smaller internal diameter, it goes down to 1.1, and then to a slightly smaller, a lot smaller diameter, a bigger diameter, it now goes down to 0.4. So as the inside diameter gets bigger, the KD gets smaller. And let's look at a larger range. Look at Aries. Okay, Aries we put into pipes where the internal diameter ranges from at the low end, the small end at 10.3, going up to 17.5. And there again, as the internal diameter gets bigger, the KD starts off at 0.7, going right the way down to 0.1. Then we take these drippers and let's put them in the same diameter. Okay, so if we look at Uniram in the top box, DripNet PC, and Aries, when they all go into a 14.4, 14.2 internal diameter, now this, as you can see, this is why I mentioned that actually the KD can go above 1. For Uniram in that diameter, the KD will equal 1.2. Aries in the same size diameter will only be 0.4. Then if we take a 16 millimeter diameter or 16.2 internal diameter, the KDs vary from the DripNet PC, which is a medium-sized dripper. The KD is 0.4. Aries is 0.3, and Typhoon Plus and Streamline X are both 0.1. Now, if we go back to webinar number 2, there we saw how the pressure varies within an irrigation block, and how in order to get the flow rate that we wanted, we have a pressure drop from where I'm pointing to now, at the beginning of the irrigation block, until at the end of the green arrows there, that's where the pressure will be lowest. Okay, and that, if you probably remember, that was to give us a 10% flow variation with a 1 litre an hour dripper. So we had 1.05 litres an hour at the top end and 0.95 litres an hour at the bottom end. And the pressure at those points was 11 meters and 9 meters respectively. And the pressure difference, therefore, is 2 meters, and that was called the pressure envelope. So we've only got 2 meters head loss to play with when we're sizing the pipe of this submain here. Now let's have a look at what the effect of the KD of the dripper lines that we use in a specific block like this. If we take a dripper flow rate, the dripper flow rate that we've got of 1 litre an hour, and the spacing between the drippers we put at 0.5 meter, and the dripper line length at 150 meters, and we apply those 3 parameters to all of these 4 dripper lines below, we will see that with DripNet PC, with a KD of 0.4, our head loss will be 1.3 meters. With Aries, slightly smaller KD, and our head loss will drop down to 1.2 meters. And with Typhoon Plus and Streamline X, who both have KDs of 0.1, our head loss would only be 1 meter. So the head loss must be deducted from the pressure envelope in the case of non-PC. Now with DripNet PC, the first one you don't actually have to worry about because that's a PC drip and it's got a much wider pressure envelope. But if we have a look at Aries, from that pressure envelope of 2 meters, we will have to deduct 1.2 meters. So 2 minus 1.2 gives us 0.8. So we've got 0.8 of a meter to use up in our submain. With Typhoon Plus and Streamline X, though, they've got a lower head loss through the dripper line. It's only 1. So if we take 1 from 2, we've got 1. So instead of being 0.8 meters head loss to be taken up in the submain, we've actually got a whole 1 meter. The KD of a dripper may generally be considered neither an advantage nor a disadvantage. The higher the KD, the more head loss, and the higher the flow variation with non-PC drippers. However, the larger the dripper is, the closer it's going to get to the midstream of the dripper line. I've just put a few diagrams here. Because you will hear it every now and again that with a larger dripper we get into this closer into the midstream where where the velocity is faster, and the contaminants, the suspended solids are less. But it's actually not really as cut and dried as that. That's why I put the diagram you can see on the right there. That in effect the midstream is actually pushed down a bit, and so your outer edge where the velocity is lower is still actually close to the dripper, but it is nevertheless you do have a marginal effect by being able to bring the dripper closer down into the midstream. So as I say here, smaller drippers have a lower KD. So should Typhoon Plus or Streamline X be chosen ahead of Aries? Not necessarily. Because bigger drippers are better drippers for several reasons, as we've seen in all the previous webinars that we've had now. So because of this, I'm not showing comparative tables of a KD. I'm just showing the KD because you see it in the data that is given, and it's important in an irrigation design, and you can see the effect on the design. But you can't really say if it's an advantage or a disadvantage, so it serves no purpose to actually show any comparisons with other drippers. Now if we get onto the dripper filter. The layers of filtration in an irrigation system comprise the following 4. We've got pre-filtration before we actually get into the irrigation system itself. And then we get primary filtration, and that's the actual body of filters that you see in any drip or micro irrigation system. And then in the field, we've got secondary filtration. That's with larger irrigation systems where your main line is 0.5 kilometer longer. And then the last line of filtration is the actual dripper itself. Now, with pre-filtration, dirt and contaminants can be disposed of before entering the irrigation system. And with primary filtration, that's your main filters, we backflush. And there the dirt is removed from the from the irrigation system. So we just reverse the flow going through the filter, out comes the dirt, and that gets taken out of the irrigation system itself. And with secondary filtration, we can also have backflushing. Sometimes it's not economically feasible and we stick to cleaning it by hand, but nevertheless, dirt is removed from the irrigation system. Now, with the dripper, the actual dripper itself, the last line of filtration, the dripper itself, neither backflushing nor cleaning by hand are possible. In the last line of filtration, the dripper itself, limited dirt removal from the outside of the dripper itself, the outside of the dripper, can be achieved by flushing the dripper lines. But much of the dirt that is trapped by the dripper filter may never be removed, despite adequate dripper line flushing. So a dripper with a smaller filter area will become covered and used up before a dripper with a larger filter area. So it follows that a longer dripper needs to last, the larger the filter area must be. So if we just look at the length that we, how long we need drippers to last, let's look at the longevity of a dripper and a dripper line. So dripper line longevity, that is related to the wall thickness. The heavier the wall thickness, the longer the dripper line will last. Dripper longevity, that's the dripper itself, that's the dripper size. The bigger, the longer the dripper will last. So by and large, as a rule, what we do is bigger drippers will go into heavier wall thicknesses and smaller drippers will go into thinner wall thicknesses. Now the categorization of the wall thicknesses, we've got thin, medium and heavy wall thicknesses. On the left hand side here, thin wall. Thin wall, we would generally say that is for a dripper line that's going to be used in between 1 to 3 growing seasons, and it's growing seasons, not year. So if you're using that on a vegetable crop, it's only 4 months, that would be 3 by 4 months. And then in a medium wall, 4 to 9 growing seasons, and a heavy wall, that would be 10 seasons or more. In that case, that's generally citrus or orchards, so that's their season is a year. Now then we apply this to the 5 Netafim drippers, Uniram, DripNet PC, Aries, Typhoon Plus and Streamline X. Uniram, that's a large dripper, and that we put in to a heavy wall thickness for 10 or more growing seasons. DripNet PC is a medium-sized dripper, and we put that into a medium wall thickness. That's for 4 to 9 growing seasons. This is, by the way, the number of grow seasons. It's not cut and dried. It's just a guideline. The Aries dripper, that's a large non-pressure compensating dripper, and that we put into a heavy wall thickness. We also put it into a medium wall thickness, and recently we've actually started putting it into a thin wall thickness. Typhoon Plus, non-pressure compensating dripper, that's a medium-sized non-pressure compensating dripper, and that we generally put into a thin wall. And the same with Streamline X. Now, drippers these days, the filter areas cover almost the whole underside of the dripper. Okay, so if we look at Uniram, this is the whole underside of the dripper there, and everything where you see those veins, that actually is the filter itself. The gap between these veins, that's the degree of filtration that we want to achieve. Same with DripNet PC AS, and the same with Aries. The filtration area in square millimeters is taken from all the slots that actually lead to the dripper inlet. Now, if you remember in webinar 1, we looked at the classes of drippers, where we have pressure compensating and non-pressure compensating. We defined as class 1, that's your high-end pressure compensating drippers. We defined as class 2, your standard pressure compensating dripper. In this case with us, it's the DripNet PC. And then with the non-pressure compensating drippers, as class 3, we defined that for Aries, our high-end non-pressure compensating dripper. And for class 4 was our regular non-PC drippers, Typhoon Plus and Streamline X. Now, if we look at the filtration area of class 1, our UniRam, where we compare it with some of our competitors' similar drippers. You can see I've put down here manufacturer A, B, and C. These are genuine drippers, and the names of these are available from your Netovim technical advisor. But you can see there that manufacturer A, their high-end PC, has only got a filtration area of 18.4. Manufacturer B, 39.7, call it 40 square millimeters, and manufacturer C is 6.8 square millimeters. And if we look at class 2, this is your standard pressure compensating dripper. And then you can see that with the DripNet PC has got a 42 square millimeter filtration area compared with 2.4 and 1.1 of similar drippers of the same flow rate of our competitors. When we look at non-pressure compensating drippers, Aries has got 49 square millimeters, and our competitors' high-end non-pressure compensating dripper has 47.2, and they have another non-pressure compensating dripper of 36.3 square millimeters. Then we have a look at our regular non-pressure compensating dripper. We've got the Typhoon Plus, which has got a 24 square millimeter. Streamline X has got 14. And then manufacturer B has actually got a larger filtration area. And then filtration C has got 16 square millimeters. So you can see the competitor B, 35 square millimeters. That actual specific dripper is actually quite a bit bigger in size than the Typhoon Plus. So maybe one could compare it with the Aries. However, we have which an Aries has got a bigger filtration area, but we've put it down as a class 4. Now, there may be a bit of disruption now. Just what I wanted to show you now, that what the screen that you saw in front of you is a UniRam dripper, where the dripper line and the dripper itself is just totally clogged up with slime. Okay, and yet this UniRam dripper is still working. I'm going to show you now why that is. So there's going to be a bit of disruption because I'm just going to go out and unshare my screen, and then I'm going to show you some 3D images. I beg your pardon. Okay, what I wanted to show you, let's just take Aries dripper here. This is an Aries dripper, and this is the inside of the dripper. Along here is the labyrinth. This is what we looked at in previous webinars. And here we see the inlet. Let's see the inlet, all the water comes through here and then goes into the labyrinth. Now let's just turn this over. And there you can see, here are the veins that serve as the filtration for this dripper. Okay, So you can see that every slot here between the vanes leads to the inlet of the dripper. These ones here are rather superficial, okay, they're a bit cosmetic, the ones that I'm pointing to now, because they're not actually connected to the to the inlet. So the filtration area is just taken from the sum total of those vanes. Now if we look at our similar, this is a DripNet PC dripper. Okay, this is part of the inside of the dripper, and that's the inlet. Diaphragm actually rests against here. And then if we turn that over, you can see that each one of these slots is connected to the inlet. The diameter of these slots is obviously less than the inlet diameter and less than the flow path diameter of the actual dripper. Now what we're going to do, it's going to show you the top of the range dripper, UniRam. Okay, the UniRam, that is the inlet to the dripper, that round circle there, and from there it's got a diaphragm, and resting against this is this flow path labyrinth there, and there's another flow path that goes on top of it. But what I want to show you is this here. Okay, this here is the filtration area, and these are the slots. So the water that enters the dripper all down here where I'm pointing to on my cursor now, all this water has to reach there, has to reach that inlet to the dripper. Okay. So let's just see how it actually, the intricacies of how this actually works. The water will flow from where I'm pointing to now to this channel here, which runs down here, and it'll flow to the right, going into this channel here. And from there, through that channel, it'll make its way down this channel to the inlet to the dripper. But at no point can any of these channels, the inlet, the grade of filtration, get bigger. It's always got to stay the same. Okay, the distance between from that vein to that vein has to remain the same, but yet it has to take on more water. So what actually happens here, you can see the water where I'm pointing to now in the middle of the dripper, it slopes away on that side and it slopes away on this side. Okay, so that channel gets bigger and bigger and bigger until it gets here. Then if we now have a look, so you've got this, the water entering this vein, and this vein slopes away and goes towards this channel going down the side of the dripper. So we've got all the water entering this vein, and then this vein, and this vein, and this vein, and this vein, and so on and so on. So the flow rate entering this channel has to get larger. So we've got to make this channel bigger, but this distance from here to here cannot get bigger. So what we've done, I'll zoom in here. There you can see a tunnel. So the water flows from here and then underneath here. You can't see this when you look visually at a UniRam dripper, but underneath there is a tunnel. So that is it really is an intricate and incredible piece of engineering when you look at how small and if you can imagine the injection molding that goes into this process. But that explains how such a dripper, in the previous photograph that I showed you, how it's just totally covered up with slime, and yet this dripper itself is still working. I go back to sharing my screen. So that dripper, as I say, is still working. So what is the impact of the filtration area on the grower? Well, simply the larger the area of a dripper's filter, the more area on which to accumulate contaminants, and the longer it will take for the area to get covered with contaminants. Essentially, The larger the filter, the longer it's going to last. And on the irrigation company, a dripper that lasts longer will place the irrigation company in better stead and better reputation had a dripper had not lasted before the filter got totally covered. Now, in summary, I'd just like to summarize the 3 webinars that we have had with the comparisons with our competitors. So in the first one, the first seminar, we looked at the turbulence coefficient. Okay, and we saw that with the UniRam, we've got a turbulence coefficient of 10.4. And we've got a filtration area of 130. Now, the exponent in non-pressure compensating drippers is always 0. So there's no point in obviously really comparing it there. But you can see in all these instances, the UniRam in these 2 factors, the turbulence coefficient and the filtration area, exceeds that of our competitors. Then I take the DripNet PC. Same thing. Our turbulence coefficient is 10.8. The filtration area is 42 square millimeters, and it's superior. Then if I go to the non-PC drippers, okay, the turbulence coefficient on Aries is 5.9. The exponent is 0.46, and the filtration area is 49 square millimeters. And then if we look at the, now remember, sorry, the exponent, sorry, just go back there, the exponent, the lower the better. Okay, so an exponent of 0.46 is better than an exponent of 0.48. So if now if we go to the class 4 drippers, Typhoon Plus with a turbulence coefficient of 7.2 and an exponent of 0.45, it is superior. But with the filtration area, as I mentioned, this competitor who has got a higher filtration area, although they've got lower turbulence coefficient and lower exponent, is actually a larger dripper. Now, these comparisons that I have shown have not been based on any sales yarn, with the exception of what I was just showing you now to a degree with the 3D images. These are all facts. The turbulence coefficient, these are all engineering facts. The turbulence coefficient, the pressure exponent, the filtration area, this is just straight facts that are come out of any hydraulic textbook. With that, I would like to thank you. I'm now going to hand over to Willem to see if you have any questions. If you have any questions, he will bring them to me, and then I will answer them if you have any.
How should KD influence your dripper choice?
Okay. What I would do is you would have a look at the actual dripper size that you want. As I mentioned, the longer a dripper needs to last, the bigger the dripper should be, and one would just has to accept that that's what the KD should be. One should never really choose a dripper based on a KD. I just put the KD in here, and that's why I didn't give any comparisons to it to show you what the actual KD means. But I can't think of any case really where one should use the KD as a factor for your choice of dripper. The choice of dripper should be based on whether it's PC, non-PC, and the size of the dripper and the longevity.
Thanks, Jerry. Then the next question is, when I flush the laterals, is there a certain time that I need to flush or any other guidelines?
Yes. The your Netafim technical advisor will be able to provide you this. It is very important. It's a very important part of the actual design when it's first done. We say that the velocity at the last dripper should be 0.5 meters per second. Now there are ways, we have got literature to show you how you can measure that by filling a bucket at the end of your, when you flushing your drippers, you fill up a bucket, and the time taken to fill that bucket, we can then it will then tell you what that velocity is and whether you've achieved that velocity. It's quite an intricate subject. The length of how long you flush for, basically you flush it until it visibly gets clean. Then the other things that one has to look at is how you're going to flush the laterals, whether you're going to do them in a gang. You're going to get the ends of your dripper lines and you're going to connect them all together into a collector manifold. That gets, you can get through your flushing a lot quicker like that, but the more you do that, in order to achieve those velocities, you need to put more flow rate into your entire irrigation system when you do that. So your irrigation system becomes more expensive. But by and large, flushing them individually, you'll get the best flush than when you flush them in a gang. But we have got literature on this where we get into quite a bit of depth, and your technical advisor will be able to explain all that to you.
Thanks, Jerry. Then the next question is, how do the quality of welding influence the dripper efficiency?
Yeah, that's a very good question. It's very important. That was actually which we covered in webinar 1. That we saw that when the dripper is put into the pipe, into the actual, it's welded to the inside of the dripper wall. There were two things that affected your turbulence coefficient. One was the sharpness of the tooth. The more sharp it is, the higher the turbulence coefficient would be. And the difficulty was with that was when you injection mold, you got molten plastic going into the end. It's got to get right to the end, and as the molten plastic comes up where the tooth bit of the mold is, it has to displace air. Okay, so you have to displace air right to the very tip. If you can't achieve that, you're going to get a rounded tip, the rounded tooth. Okay, and you will therefore not get your required dripper efficiency, your turbulence coefficient, and you have to add on more teeth. In the same vein, when you get those sharp teeth and you weld it to the inside of the, you get your sharp tooth, you get your dripper, and you weld it to the inside of the dripper, the less efficient is that welding, because whenever you weld anything, whenever you weld any thing at perpendicular to another surface, you're going to get some distortion, some roundness. Okay, you're never going to get it totally flush. So when that is welded there, the more you can minimize that distortion as a result of the weld, then the greater will be your turbulence coefficient.
Jerry, then the last 3 questions are all to do with each other. The 2 questions, we've received 2 questions about CNL drippers. The first CNL dripper question is, how does CNL dripper with 4 arrows for pots compare also for design?
I'm not sure I actually understand the question. How does a CNL dripper with 4 arrow drippers for pots compare also for design? Oh, okay. If we're talking about the actual pressure required for a CNL dripper with those arrow drippers being put onto the design, if that's what you're referring to, when we design for that CNL dripper, the CNL dripper itself has got a minimum flow rate. generally, it could be anything 3, 4, 5 meters. So you have to put that minimum flow rate, the CNL drippers, into your design. Then after that, you have got your tubes, your 3 by 5 millimeter tubes. They'll have friction loss. You have to add that. But I can just tell you right now, regardless of the flow and regardless of how long that tube is, it's actually minimal. You can basically discount the friction loss that goes into that submain, into that flexible tube. Then that flexible tube, from that flexible tube, you put in an arrow dripper. And that arrow dripper is a non-pressure compensating dripper. And to achieve the flow rate that is required in that non-pressure compensating dripper, going back to webinar 2, where we saw the relationship between flow and pressure, that relationship applies to arrow drippers. So let's just say you have got a 4 liter an hour CNL dripper, and you split that 4 ways into 4 arrow drippers. So each one of those arrow drippers has got to get 1 liter an hour through it. That 1 liter an hour, you then have to look at the Q times K times P to the power of it, that formula that we showed you with the exponent, and you have to see what pressure is required to get that water through that arrow dripper, and that pressure on the arrow dripper has got to be added to the CNL dripper, and the two together will be the pressure that you must design at the inlet of the CNL dripper. Now, if that sounds a bit long-winded and complicated, again, we've got literature where we've already worked that out for you. So generally, we've got most of the permutations that are required of whatever arrow drippers you put to a CNL dripper, that you will be able to have the minimum pressure required to operate that. I hope that was actually how I've answered your question. If it's not, please go ahead and rephrase it. Are there any other questions, Willem?
Yeah, then there's the lifespan for CNL drippers and the arrow pots. What is the recommended replace in how many years?
Okay.
CNL.
Okay, the longevity of CNL drippers and arrow drippers primarily depends on the arrow drippers. That's in my experience. Whenever we use these, we use fertilizer enriched water, either intermittently or continuously. So you've always got fertilizer and acids. A natural CNL dripper itself, the only thing that I've seen that degrades in that would be sometimes excess chlorine. I've seen degradation in CNL drippers, but that's been very, very infrequent. However, with arrow drippers, what I've seen is the arrow drippers themselves, what I just mentioned in the previous question, we do have a minimum pressure that you need to put into an arrow dripper. In fact, the example I gave just now, where we had 1 liter an hour. In fact, 1 liter an hour is the real bottom end of putting it through an arrow dripper. That's our 1.6 liter an hour arrow dripper. If we take the 1.6 liter an hour dripper, that 1.6 liters, like we mentioned in the webinar 1, the nominal flow rate of all of our drippers is the flow rate at 10 meters. And when we take a 1.6 liter an hour dripper, and we only put 1 liter an hour through it, the pressure required to achieve that 1 liter an hour is 4 meters, okay, just under half a bar. If you should try to put less than that, the required pressure will now decrease. The velocity that goes through the labyrinth of that arrow dripper will also decrease. And in our experience, my experience, depending on the quality or the efficiency of the dissolving of the fertilizers, that can be problematic. Okay, I've seen, just for argument's sake, I've seen once calcium nitrate, which was dissolved into the irrigation water, and I'm not a fertilizer fundi at all, but iron was used to bind it, and that iron was precipitating out in the irrigation water, and then we had iron then choking up the arrow, the arrow drippers. So a lot of this was to do with the actual dissolving and of the fertilizers. And basically, we found that the safest, as long as you get 0.4 of a meter minimum going through the arrow dripper, then you're safe. And then in terms of how many years, I mean, I can't really put a number on it, but certainly we have, I know by experience, I know a lot of systems like this that are going in excess of 10 years.
Jerry, and then maybe the last two, I think you can answer as one. The first part of the question is, how long is a dripper supposed to last? And then Henry asked, if you've got blocked drippers, what is your recommendation on treatment?
Okay. How long is a dripper supposed to last? Okay, well, as I mentioned earlier, the longevity of a dripper, how long it's supposed to last, is a bigger dripper lasts longer than a smaller dripper, and it's for that reason that we put larger drippers into heavier wall thicknesses, and the heavier wall thicknesses go on to longer season crops. So if we go at the one end where we've got the thin wall, we said 1 to 3 seasons. Okay, so if and within the thin wall, we've got two drippers. We've got Streamline and the Typhoon Plus. The Streamline is a little bit smaller than the Typhoon Plus. So 1 to 3 growing season. Let's say vegetables. Vegetables is generally a 3-month crop. So sometimes you'll get 2 of those crops in a year. Sometimes, if it's warm enough or you've got a bit of undercover, then you get 3 in a year. So where I say 2 to 3 growing seasons, we will use a thin wall, and we would tend to use that smaller Streamline for just 1 season, and then we'll use the larger Typhoon, which also goes into a thin wall, for going towards the 3 seasons. By the way, we've just I'm just going to tell you a bit about sales at the moment. We just introduced a Streamline in a very, very thin wall. It's on its way here, and it'll be here in September, where that is just single. It's called SU, single use. Now, when we go to the other extreme, we've got the heavy wall. The heavy walls are 1 to 1.2 millimeter, and that will go into your orchard crops. We say 10 years. There are orchards everywhere where you can see 15, 16-year-old drippers there, but you must have a bigger dripper. Now, then when you just go in between, okay, I'll just give you an example of medium wall. We're doing something at the moment with low flow drippers. Now, that big dripper, we'd like to do very low flow pressure compensating drippers, and we'd like to put them into orchards. But the low flow dripper in Uniram, we don't have a very, very low flow. Well, I'm talking about 0.4 liters an hour. But we do have it in DripNet PC. Now, if we were going to use a heavy wall with DripNet PC and put DripNet PC, which is a medium-sized dripper, into that heavy wall, the heavy wall itself is going to last 10, 15 years, no problem. But the DripNet PC, because it's such a smaller dripper, we don't know that. So while we are using this at the moment in orchards, citrus macadamias, we're taking that dripper and we're putting it into a medium wall thickness with the full knowledge that we're going to have to replace it maybe in 5 or 6 years. We don't know. I hope that maybe answers the question. The other one is, what is the recommendation for the treatment of block drippers? Gee, that really is it's a long story. We would spend a couple of webinars just covering that subject. There is no like one chemical that cleans everything. There's no handy Andy that can go and clean everything in drippers. You've got to look at the actual, what the reason for the blockage is, and then basically you treat the symptoms according to the cause. But please get hold of, you can get hold of me if you like, and also your irrigation designer. So your your technical advisor, who will be able to give you all our literature with treatment of block drippers.
Jerry, and then the last one is back again with the KD and the CNL drippers. All that literature, the question is, so we will find KD Netafim literature for CNL drippers. The 6.4 liter per hour CNL dripper envelope will be minimum 4 pressure and maximum 30 meter pressure.
Okay, the KD for CNL drippers, if you're talking about the button dripper that goes on the outside, yes, we've got that in the technical, because all you've got is the barb that goes into the actual dripper. So the effect of that barb we have in our literature. This 6 liter per hour CNL dripper envelope will be minimum 4 meter pressure and the maximum. No, the pressure envelope, that is from the highest pressure of your block to the lowest pressure of your block. For an act, that's the inlet pressure of the dripper at the beginning of the block to the inlet pressure at the dripper at the outer block. That's the pressure envelope. But the pressure itself, that is the maximum dripper. I'm sorry I don't have the figures in my head, but we do have it in the in our literature, which tells you the minimum pressure of a CNL dripper and the pressure required for the arrow dripper, and you put the two together, and just basically, I could be wrong, but basically it's between 2 to 2.5 bars. Okay, 2 to 20 to 25 meters, but it can come down lower than that depending on the CNL dripper that you're using, its flow rate, its minimum operating pressure, and the number of arrow drippers that you're using to connect it. You can't. I know I'm just generalizing when I said 2 to 2.5 bars.
Thank you, Jerry. We've got no more questions.
Thank you. I appreciate those questions. Some of the questions, I appreciate that people are listening, and it makes it interesting and encourages me. Thank you very much. Take care. God bless.